Yes, this works. Okay, let's start the afternoon AI session. I'm Norbert Breining from Archive. I'm very happy to see a few people here. We have a lot of talks going on. Let's jump directly in. A talk by Dipti Man is fine on Flink SQL and PyFlink. I'm looking forward. So please welcome the speaker.
Thank you very much.
I will solve the streaming.
Yeah.
Okay, sorry.
So first session after lunch, it's my job to make sure that you don't fall asleep. And so I'm going to talk about Flink or Apache Flink and a little bit of Apache Kafka as well. For anybody who has done a little bit of real-time projects, programs, Apache Kafka stores streaming data and lets you quickly query and get data out of the stream so that you get real-time information. A sale, let's say, happening at a retail store, or an IoT sensor sending some temperature inputs to some actuator, a robot which is getting information from a sensor, and then, let's say, it tries to move one of its limbs. These are all happening real time. Your Grab, you get updates from the driver or the riders. Everything happens real time. And most of these are happening on Apache Kafka. So what we'll do is, today my focus is not really Kafka, but I'll spend like 3-4 slides on Kafka. And then I'll move into Apache Flink, which lets you extract insights from these streams in Kafka, so that you could actually tell that how many instructions have come in the last 5 minutes, how many sales have happened from workstation 2 in a retail store, how many customers were onboarded by a certain cab booking app in the last like 15 minutes and stuff like that. Could you please add it for me?
Okay, sorry.
That's okay, thank you. So let's jump right in. So it would be a very quick introduction to Kafka, and then we'll fall through Flink.
Debian basically says that the things should be we have a few areas that we will always be free, and we should be used for whenever there's some things like that. You can check it out. It's the core value generator, and it's generally served by the everyone, and we will follow. Sometimes follow the gatekeepers of the software, because everything is shipping everywhere is the software, except a particular exception with conflict member that we need to run settings in terms of these users must have and so yeah. So why we do this? And as in so it's people who care about freedom and privacy.
But it's the write-ahead log or wall, as we call it. Messages are added like absolutely very, very quickly. And these messages could be namespace isolated into logical constructs called topics. And a Kafka topic is just like a database table. So it could be a sales, an orders, a clicks, or device statistics, etc., so that we could use this as tables later on. And then each topic is broken into partitions, which are the unit of parallelism. So if my topic needs more streams to ingest, I would increase my partition. Very high level how Kafka works. So we have brokers or servers, which are nodes where this streaming data is stored within a topic, within a partition. There are producers which sends data into these nodes, and then there are consumers which takes data out of these nodes by running a forever running polling loop. So it just keeps on running. There are many other nuances within Kafka. So the consumer might fail. If it fails, how does it know from where does it start again? But then for today's talk, that's not really what the point is. Today, I'm going to focus on how do you analyze and transform and write queries on these streams. But those are all possible as well. So there are very well-defined mechanisms of handling such failures within Apache Kafka. Now let's jump into Apache Flink, which is today's talk. And the rise of Flink has only happened because today's consumers demand real-time data. There is a need to have real-time data. There is a need to know when a sales happens right there, right now. And the downstream application need to understand what exactly is happening. So the point is we need to inject those insights within this streaming data, which is stored by Kafka. So Apache Kafka, while it serves as a stream storage, Apache Flink works as a stream processor. Can I use Python to do that? Absolutely. So that's what we are going to talk about. Now, quickly, some refresher on basics of what a stream consists of. It consists of events. So when we talk about streaming data, we actually talk about event streaming data. What is an event? Event has a what and a when, a state and a timestamp, so that you understand what's happening with the precise timestamp of when it did happen. These are some examples. So for an IoT sensor, it could be a device ID and then temperature, humidity, motion. This could be one of the event data. There could be business process change events flowing through a system, like when did the customer was approved for a loan or not. It could be clickstream data, which is keyed by a event ID or an user ID, and you have all these notions of who has done what. So event at a minimum, we have a key and a value. Now let's talk about, so we understand what an event is, right? So it's a JSON file with, let's say, a key and a set of values, and I would have a timestamp on it. Then a stream is nothing but a table. Let's just construe, let's just imagine this as a table now, where all this streaming data keeps on getting added in an unbounded fashion. So unlike a database table, the change here is it's unbounded. There is no bound. So if you run a select count star, it would give you non-deterministic answers. If you run it like 5 times, it will not give you the same answer. So that's why we call it an unbounded stream. Now the question is, how do we transform the stream? How do we extract information from the stream? What we do is we take the stream from now and go backwards in time and put some time boundaries, 5 minutes, 1 hour, 1 day, and try to extract information out of it. So the design motive is to query the stream. How do I query the stream? How do I get to know information which is happening right now, while that stream keeps on going in future? So that's precisely what Apache Flink does using Python and SQL. So both Python and SQL are supported in PyFlink, and it's a relational API, if I might say so, for Flink, where both gives you the same optimized AST. If you do an explain plan, if you're aware of what an explain plan is, it would give you the same exact logical steps that the compiler, the SQL processor would follow in terms of running the query, whether you run it using Pythonic API or whether you run it as a SQL. A quick example of how it might look like in production. So I might have like PV cells in my photovoltaic cells for solar, tapping solar energy in a field. I pass it to an aggregator which takes all these values. It passes it to a Kafka topic. I apply SQL functions using Flink. I get the aggregated or transformed streaming data in another Kafka topic. I attach a Kafka sync connector. It passes the data to an Elasticsearch index, and I have a Kibana dashboard which, let's say, updates and refreshes the dashboard every 5 seconds or every 10 seconds. So you get real-time updates on what exactly is happening. A Flink cluster is an MPP, massively parallel processing cluster, where you have a program which acts as a client. It takes your inputs, uses Apache Calcite, which is another open source SQL query optimizer and planner. It converts your query and your Pythonic APIs into something known as a job graph, a data flow graph. That gets pushed to a job manager, and the job manager spawns all these workers to run these transformations. It's intelligent enough not to really go deep into the infrastructure, and it could chain all these operations. Like here, I have a source operator on which I'm doing a map. Source operator could be a streaming data producer, like a Kafka topic. I put a map operation on it. I get a one-to-one transformation done, and then I do a group by using a specific primary key, and then I pass it to a sink. Flink would automatically chain these operators. But the real power to a developer comes from these two APIs, the Flink SQL API and the table API. So these are declarative Pythonic DSL APIs, which you can use with Python. And then it runs on your streams, and you can write your Python jobs right there, right now. A little bit deeper into how that happens. So a Kafka stream is converted into something known as a Flink dynamic table, and we call it the stream table duality. So what is a dynamic table to a Flink is nothing but a Kafka stream. So all this data which gets appended in my Kafka topic starts appearing as one of the rows in that table. So look at this one. I have user creation time and the URL which the user clicked. So what happens is the dynamic table actually starts inserting these rows one after the other, one after the other. And then we could run our Pythonic table API transformations or Flink SQL right on that table. Flink SQL is ANSI SQL compliant, and Pythonic DSL, the table API, is absolutely Python, like Python API. And what happens is your queries start running on that dynamic table, and it creates another dynamic table as a result set. So if I want to do, let's say, some filters, I want to select column A, column B, group by column A, and maybe put some aggregation function on column B. It would create dynamic table as an output, as a result of this query. And since there is a stream table duality, that table would exist to the downstream application as a Kafka topic, another Kafka topic. So you could pull that data and then update any dashboard if you want. So dynamic table is the core concept. It changes over time. If you query, it gives rise to another dynamic table, and the query runs perpetually unless you decide to stop it or unless the infrastructure fails. If the infrastructure fails, Flink is intelligent enough to keep a checkpoint, and that's automated. You don't have to do anything about it. Whenever the infrastructure comes back again, it starts reading from the last offset. So how do I query? How do I write these queries on a Flink dynamic table? Very simple, just as a simple SQL aggregation. So I could do a select user count of URL as CNT from clicks group by user. And look at the right-hand side. So what exactly is happening is the right-hand side Flink dynamic table actually keeps on adding the aggregated value. So Murray comes 1, and then Bob, and then Murray is 2, the count goes to 2, and then Liz 1. Now, stream table duality is what I've introduced just a couple of slides back. So you could have tables which could have two types. One could be append only. So your aggregated table, after running the Flink transform, could just have just the rows which my original Kafka topic had, maybe some filters applied to it, but then it's still append only. So the rows keep on getting added. But then look at this one. So here what happens is, if I'm doing a negative sale, the bestseller table on the right-hand side actually gets updated with the hat count. Now, think about it, how it happens in a SQL, like an RDBMS or maybe a batch, OLAP, or a data warehouse. So we do an upsert, right? Here, it's still an upsert, but it actually happens in 2 steps, because you need to retract one of the events from this Flink dynamic table. So there are 2 operations, a minus update and a plus update. Now, do you have control over it? Yes. You could write listeners to listen to minus use and plus use, minus size, plus size, etc. So it could have either an append only stream, or it could have an upsert or a retract stream as well. The second most important aggregation function
after the regular count, sum, average, mean, max, which I just showed you by the group by, is windowing, which is a very, very important. It not only belongs to Flink, it's for any streaming data. What you could do by windowing is you could put time barriers for analyzing this data. So I could actually ask questions: how many vehicles did cross this toll booth or a camera where all these vehicles are tracked every minute or every hour? So I could have questions like, tell me the sum of vehicles passing this sensor camera every hour. Or I could actually take it up a notch and I could say, tell me the number of vehicles passing this camera every hour and keep me updated on that value every 15 minutes, which is like a moving average, like a simple moving average, not the exponential one. So those kinds of windows, the first one is called tumbling window.
A simple moving average, not the